So in this video, I'll be explaining about representation of stresses. Let us consider a bar that is hanging from a fixed support as shown in the figure and is acted upon by an axial force P. These are the coordinate system and axis that I'm going to be using in this video. So any point on this bar is represented as a square, and in 3D it will become a cube, right? We know that stress is denoted by sigma. Then now, in order to explain further, I will establish what a tensor is. Okay, so I believe you all know what a scalar is. A scalar quantity is something which has a magnitude like mass, weight, okay, etc. Height, right, etc. Weight, in certain cases, it may be referred to as a vector as well, but in general, weight is also a scalar. Okay, and vector is a quantity which has magnitude as well as direction. Example is displacement, force, velocity, etc. Now, what is a tensor? A tensor is a quantity that requires n number of parameters to be defined or established. Okay, so what are these n parameters? Let's see. So in case of a scalar, the number of parameters that are required x other than magnitude, pardon me, other than the magnitude itself. Okay, other than magnitude, what are n other parameters that are required to completely define this quantity? Okay, so that is a known as a n order tensor. Okay, nth order tensor. Here you can see that a scalar, other than magnitude, it requires zero other parameters to define it, right? Mass, it requires only the quantity, that is 70 kgs, 70 kilograms, 70 pounds, that. So a scalar is a zero order tensor. Vector, it requires one more parameter, that is direction. Displacement, 50 meters towards north. Force, 50 newtons push, 50 newtons pull. Okay, so vector is a first order tensor. Okay, all right, so now you have a grasp of what a tensor is. Now we can move ahead and look how this can be applied to a stress. This cube here, a stress acting on this plane. Remember that a point in any element, like any machine element, a structural element, a point is represented by a cube. Okay, so I will be drawing cube and it should be considered as a point inside a element, machine element, or a structural element under study. Okay, in this case a bar. Here sigma. Now sigma is acting on this plane, right? Let me shade it, this plane here. Now what characterizes a plane? A plane is characterized by the normal, right? A plane is defined by its normal. So the normal to this plane is in, remember the coordinate system, y, x, and z. So this direction is x. So this plane is defined by the normal in x direction. So first term is this normal's direction, right? Right? And in what direction is this stress acting? This stress is acting in x direction again. So first subscript denotes plane on which stress is acted upon. Second subscript shows direction in which stress is acting. Right? Right? Okay. Now let's see ahead, and then let me define this as well. Explain this as well. This is a force P, and then this is an element. This element bar, this bar is acted upon by an axial tensile stress, right? P, due to the force P. And this axial tensile stress can be represented at a point, this point, as like this. We draw a cube, and then this sigma, and this is sigma. So this is acted upon by an axial tensile stress sigma. And what are the parameters that define sigma? Sigma, the magnitude of sigma, that is P upon the cross-sectional area of this bar, and the plane in which it acts, the plane in which this stress acts is this plane, and the bottom side is this plane, right? So direction of the normal of this plane in which the stress is acting is, you can see, it's in y direction, right? So y, this is also in y direction, right? Positive and negative y doesn't matter, it should be in the y direction. Okay, so y, and the stress itself is also acting in the y direction, so second term is also y, right? So this is sigma yy, right? Okay, I hope this is clear. Now sigma, let's see the same for the tangential stresses, the shear stresses. uh, so let me draw the element here. We'll see that this plane, the tangential stress acting on this plane can be denoted right here as sigma, right? Now this sigma, the direction of the sigma is in x direction, right? And the plane in which this sigma acts, the normal to that plane is in y direction, right? You can see this is the plane's direction, and this here is the direction in which the stress acts, right? Y, x, right? Now it's generally, shear stresses are not denoted by sigma, they're instead denoted by tau, Greek letter tau. So tau y x. And shear stresses are always in pairs, right? Always act in pairs. All stresses always act in pairs, right? The sigma yy, there's a sigma yy in the corresponding opposite plane as well, right? So this stress, the opposite direction stress, to be balanced here is like this. This is also sigma, so sigma yx. This again the sigma, or better you call it tau, we call it tau. So this tau is equal in magnitude, like this sigma yy and this sigma yy, they are equal in magnitude but opposite in direction. Similarly, shear stresses are equal in magnitude but opposite in direction, right? Sigma yx tau. They inclusively have an effect on body, and that effect is the shear deformation of the body, right? Now tau, the direction of tau is x direction, right? The x direction. And the plane on which it acts, the normal to that plane is in y direction, right? So this is tau y x, same, or sigma y x, right? Same, tau y x and sigma y x. This is the plane, right? Okay, I hope this is clear. So now I would like to conclude by relating the two things that I have taught you today: the representation of stress and tensor, right? So what you can see from the representation of stresses is that stress requires two more two more parameters other than magnitude, right? And any quantity that requires n number of more parameters other than the magnitude is known as the nth order tensor. So stress is a second order tensor, right? So in the further videos, I will be explaining about the principle of complementary shear stresses, in which this representation will be even more clearer. So till then, keep learning, keep watching my videos, and please do like, share, and subscribe to this channel. Thank you.